So now we're going to address a very important question, okay? It's the first question that we're going to ask regarding rational functions. And it's the first question that we're going to answer, okay? Besides what they were. So what is the domain of a rational function? Well, we're going to let our rational function f of x, in this case, be n of x divided by d of x, where n of x is the polynomial and d of x is a polynomial. But by writing it this way, it's more compact. But if you want to in your notes, you can write it just the way we wrote in the preceding definition. Okay, you can see that it's exactly the same idea, because here I've written n of x to represent the polynomial on top and d of x to represent the polynomial on the bottom, and I don't need the specific form to make the following statement. I want to ask you a question. What can never happen in a fraction? I want you guys to think about it for a moment before we look at the actual statement that I'm about to write. And you may already know what I'm talking about. So I want to ask you just one more time before I mention it. What is impossible in a fraction? What can we never have happen? What can we never have happen in a fraction? The bottom can never be 0. The denominator can never be 0. So with that observation behind us, we can see, aha, the domain of a rational function excludes all values which cause the denominator to be 0. Because as we know, we can never have a 0 in the denominator. So that motivates us. So that motivates this definition. This criteria. The domain of a rational function is basically all the real numbers except those which make the bottom to be 0. Okay. So having said that, we're not prepared to look at some examples. So let's look at this one. What is the domain of this rational function? Now, if you notice, this is barely a rational function, but it is a rational function, right? It has the polynomial on top is just the constant polynomial 1, and the polynomial. So strictly speaking, that's not normally what we would think of as a polynomial, but it actually is a polynomial if we want to look at it in the most broad sense possible. Okay, it's just a very trivial polynomial. On the bottom, we have also a polynomial, also very trivial, but not exactly as trivial as the one on top. But we can see that this is essentially, in other words, one of the simplest cases where we can ask the question, what is the domain, right? Okay. And what we want to do is we want to eliminate all values of x that make the denominator 0, right? That's what we want to do in our brain. We want to eliminate all values of x right? Well, what's the denominator here? Well, the denominator here, or let's call it d of x, to be consistent with our notation here. Okay, our d of x is just x. Well, we know that x equal to 0. Under what condition is x equal to 0? If x is 0. Okay. So we could say we know that that d of x equal to 0 would imply x equals to 0, because of course d of x equals to x. But we know that x equals to 0 if and only if x is 0, because of course the bottom, the denominator, is just x. So it makes our life easy. So how would we express that? Well, the way we would express that is that our domain of this function, is going to be from negative infinity all the way up to 0. And then we're going to put parentheses. Why parentheses? Because the parentheses says that we're going to get as close as we want to 0 without including it. And then I'm going to union. That's going to be like my glue to hold the pieces of the domain together. and then 0, comma, infinity, like this. Okay? Okay. So that is the domain of this very simple case. Okay? So now we're going to look at this example. We want to find its domain. Okay? And what are we going to do? We're going to eliminate all values of x that make the denominator 0. So here, how do we get the domain? We eliminate all values of x which make the denominator 0. So if we let d of x equal to x minus 5, right, which is in keeping with this notation here of the denominator polynomial being denoted d of x, then we want for d of x to equal to 0. Okay? Why? Because if we find the values of x that make this true, then we will not eliminate those values. But if we want d of x to be true, then this means that x minus 5 must be equal to 0. Oops, I just miswrote that. That's terrible. Okay. Right? So I'm going to put here then instead. Yes. So if we want d of x to be 0, then what we want is x minus 5 to be 0. Now if you look at an expression, or an equation actually, like x minus 5 equals 0, you just simply have to add 5 to both sides. And you can see that if x equals to positive 5, then the denominator will be 0. And we know that that's a no-no. So we know that that's going to be eliminated from the domain. So we can now write our domain as follows. Okay. Our domain is going to start at negative infinity, right? It's going to go all the way up to 5. Okay. And then it's going to be parentheses. And then it's going to be union. And then it's going to be open parentheses, 5, comma, infinity. Like this, and then close parentheses. Okay? It's not a bracket, it's a parenthesis. Sorry about that. I didn't want it to look like a bracket at all. So this is the domain. You see, we exactly omitted the value of x that makes the denominator of this rational function 0. Okay? Okay. So another question is, what about an example like this? Okay? Now, you might say, David, this looks just like the other examples. We're going to set the denominator equal to 0, and whatever x's we find, we're going to eliminate them from the domain, right? But this example is special because, well, it's not that special, but it begins us on a path of some interesting questions. So, for example, for those of you who have learned about the difference of squares perfectly, you guys might observe that the denominator can be factored. So in other words, some of you might ask me, okay, David, but I can rewrite this as x plus 2 over x plus 2 times x minus 2, right? I'm applying the difference of squares formula to the denominator. So if you multiply these two factors out on the bottom, you will regain the same denominator. So that question is not, so that question of whether I can rewrite, or not question of whether, but the question of, is this rewriting legitimate? Of course it is, right? This bottom is identical to the bottom here in an algebraic sense, okay? But this leads to something that we haven't seen before. Look here. When I factor it, I can see that I don't want to use the phrase, but we're going to use it, cancel the x plus 2 from the top and the bottom, okay? We think about that for a moment, right? That's true, right? And so a lot of you might say to me, well, David, if I look at it from this perspective, then am I only going to eliminate 2? Or am I also going to eliminate the negative 2, which would have made this factor 0? In other words, the question that arises with an example like this is if the rational function can be simplified algebraically to a simpler form, and if in so doing some of the factors of the denominator in the original form, which would have become 0, are no longer in the final form, do we also have to exclude those Do we also have to exclude the zeros associated with those factors from the domain, or do we only eliminate the zeros of the factors that remain in the simplified form? Okay. Notice that question, right? So, in other words, to restate it using this particular example, are we going to eliminate the x equals -2 and the x equals 2 that make both of the factors of the denominator? Wait, what? Oh, yes. Are we going to eliminate -2 and +2 from the domain, which we would need if we looked at the original form? Or are we only going to eliminate the 2, which makes the simplified form 0 in the bottom? And the answer, we're going to eliminate them both, always, okay? Okay, so here, the domain, we're going to eliminate -2 and +2. So it'll be -infinity all the way to -2, union, -2 to 2, and then union 2 to infinity. Okay. Okay. Yes. So that's number one. Okay. We saw that the interesting thing about this example was that the rational function could be rewritten, and that in its rewriting it could be simplified, and that complicated the question of what we consider our d of x for the purpose of finding the domain. The question being whether it was the original d of x, in our case, x squared minus 4, or whether it was the new d of x, x minus 2 in the simplified form. And the answer was, and is, and shall be, that the d of x, the denominator of x that we're considering, is the original one. And we will eliminate all the values of x that make that original denominator 0, and that's what gives us the domain. Okay? Now, I want to discuss a brief side point here. You might have noticed that I kind of felt a little bit of trepidation at the thought of using the terminology of canceling the x plus 2 from the top and bottom. Okay? Now, you might say to yourself that this is language that's commonly used for it, and it is. It is commonly used language. There's and under the assumption that the individual knows what they're talking about, it's of course understands what it means as well, then of course there's no problem in using that language. But just as a brief discussion of that, I want to have a brief discussion of that here, so that you can know what we mean when we say we cancel something, right? So here, let's look at this expression, x plus 2 divided by x plus 2 times x minus 2, like this. Write the expression for f. Look what I want you to see. I could see this, if I think about it in my head, as the product of the fractions x plus 2 over x plus 2 times the fraction 1 over x minus 2. I think you'll agree with me with this. How would we, so imagine if we didn't have this for a moment, and I wanted to multiply these two fractions, I would say, okay, the product of two fractions is the fraction whose numerator is the product of the numerators, and whose denominator is the product of the denominators of the fractions being multiplied. What's 1 times x plus 2? It's x plus 2. What's x minus 2 times x plus 2? It's, of course, x minus 2 times x plus 2. So you can see that, in fact, this expression is legitimate. Is a legitimate factorization of this expression here, okay? But I want you to notice something here. What is this expression on the left? The expression on the left, namely, x plus 2 over x plus 2 is a fraction whose numerator is equal to the denominator. And what does that mean? We remember when we were discussing fractions that any fraction with the same numerator and denominator equals 1. And so we can see that now, and I want to make one caveat here. That's only true, and we're only considering it if the bottom of this is not 0. So in other words, this is equal to, let's say, the number 1 times 1 over x minus 2, but where? For all the x not equal to -2. because if it's -2, it'll make the bottom of this fraction 0, and then we don't have any thing to say about that. We just specifically eliminate that value of x because it makes this fraction undefined. Okay, but for all of the values of x, we can see that this is equal to 1. And what's 1 times any number or any expression? It's that expression. So under the same caveat as this one, which goes here, we get that this expression does in fact simplify to 1 over x minus 2. Okay? And so the main point I wanted to make here is the following. When we say that we cancel, okay, a term like x plus 2 from the top and bottom, we're really exploiting these basic properties of fractions. Okay? Number one, that we can rewrite it like this. And number two, that for all those x where this fraction is defined, a fraction with the same numerator and denominator is equal to 1. And of course, the fact that 1 times any number or expression gives us that same expression back. Okay? In particular for all x not equal to -2. And by the way, that's why when we were calculating the domain of this one, we had to maintain the 0, the x that made this term 0, as well as the x that made this term 0, instead of only the one that made this term 0 in the simplified form. That's why we had to keep both x values that made the original domain polynomial 0. That's why we had to exclude both of those values. Oh my god, I got that all jumbled up now. Just to recap, looking at this explanation here, you can see why we not only remove 2 from the denominator, from the domain of this rational function, but we also have to eliminate the -2 that makes this factor 0. That's why we had to do that. Okay. And so now what we're going to do is, let me look at this here. And so now we're going to look at what does it mean, or what is the significance of some, or not. Well, now we're going to look at another interesting thing. Okay.